to be your host for the day. I'm the general manager of electric vehicles and analytics at Bidgely. And so this is the perfect topic actually for me, perfect intersection between electric vehicles and analytics. We're going to talk about debunking myths around EV detection, specifically using artificial intelligence. So to start out, for those of you who are not familiar, potentially not as familiar with Bidgely, I just want to set the foundation of who Bidgely is for you. So at the end of the day, we're an energy intelligence company. For over 11 years, we've been looking into behind the meter insights and specifically disaggregation, which we'll talk about, which means we're detecting appliances in each customer's home and actually understanding what those appliances are doing. That's our platform of energy intelligence. We actually then aim for strong outcomes across these three categories using that platform. So first and foremost, to turn customers into happy and engaged energy partners. Second, to build and manage a modern grid that's resilient and responsive. And finally, just to allow the utility to run data-based programs and understand how their operations are with data in the forefront. So what are we going to do in today's webinar? Obviously, we can't cover everything that Bidgely does, but we're specifically going to focus on our EV detection and estimation using disaggregation. We're going to focus on the common use cases. Why do you need that data? And how might you use it? We're going to dispel common myths about using AI for EV detection. And finally, I am going to spend a little bit of time giving I'll say a simplified data science lesson to help everyone understand, hey, what is important in terms of disaggregation and how can I measure the effectiveness of artificial intelligence? So now, before we get all the way into the presentation, I do want you to use that link that I sent, go to menti.com. And I'm just interested to learn, why did you join the call today? What are you interested in learning? I'll give everyone about a minute to respond. Keep in mind that if you put something up here, I'll make sure I address it. So if you're really anxious or excited to learn something, please go ahead and respond on the Menti. Good first response, learn how AI can help with managing a growing number of EVs. I promise I'll definitely do that. Disaggregation, yep, how it really works. Oh, I like this one, potential for level 1 charger identification. Spoiler alert, we can do that, but I'll talk to you about exactly how we're doing it and what's the difference between level 1 and level 2. Oh, another great question, is hourly data granular enough to detect? And so we'll touch on this as well. And same with the next one. Thank you for everyone who did participate. Great questions. We'll talk about everything that you've mentioned here, including what data is required. So I will say hourly data, granular enough. We'll talk about what it means when we say is 15 minutes, 30 minutes, an hour enough. And we'll talk about how we can use that and what to expect from that level of granularity. All right, before we get into those technical pieces, so I'll let you know that that's actually going to be second in this deck. We will talk about that. I actually want to start with just the high-level use cases, because before we get into how cool the technology is, I think it's important to level set. Why do you need to understand where electric vehicles are? Why do you need to understand their load shapes? And talk about what different utilities are doing with this type of data. And then I want to hear from you, what use cases are you interested in? What are you already doing? What aren't you doing? And so the use cases are really fairly equally divided between grid and customer. On the customer side, the biggest one we see, or at least most interested, is in targeted marketing for EV programs. Why are you interested in targeted marketing? Well, really, modern marketing focuses on honing in on your audience. Essentially, it's going to increase your conversion rate, lower your marketing spend. The fact that we can identify level 1, level 2, level 3 chargers, it enables utilities to market in the right places for their make-ready programs, their managed charging programs, EV rates, or even whole home rates. Customer engagement for EV owners. So an important thing about this engagement is you don't want to have the same type of engagement for an EV owner and a non-EV owner. For example, if you're helping the customer understand their bill but don't know that they have an EV, you're missing a big part of the bill for them. And so we actually, using our disaggregation, offer tools and tips so that the user can understand ownership and understand their charging patterns while ultimately minimizing their charging cost. And then finally, on the customer side, is really the program planning aspect for the utility. So what is the potential for a managed charging program? Or what is the potential for a time of use rate? And then how could I actually design a program based on actual data? On the grid side, we see 3 other types of use cases. First is just infrastructure planning, both for chargers, but then also for actually grid assets like transformers or feeders. It's important to know where EVs are located on your grid, but even more specifically, understand the load shapes and the load patterns that how they're charging. It's also important to identify hotspots. Essentially, we can't just upsize everything on the grid, right? That wouldn't be cost effective. And honestly, we really don't even have those devices available. And so it's important to identify hotspots and then plan for non-wires alternatives. It's also important to just understand the growth analysis. So if we're seeing over the past 3 years this level of growth, we can understand that growth curve and analyze how behavior from customers may be changing or how that growth may be changing. Finally, forecasting. This is an important one because right now I think we all expect EVs to just continue growing at this fast rate. We do know policy and especially different geographic trends are going to affect this. And so when you forecast, you have to think about how you evaluate low, medium, high growth scenarios, and then also understand what are certain customers' propensity to actually purchase. So these are the 6 use cases that I framed up today and that we see as most common. But what I'd like you to do again, please engage. And what we're going to do is tell me which one you're most interested in. And then also tell me if there's some other use case you're interested in with that other bar at the bottom if I didn't hit on it, because I always love to hear new use cases. So if everyone can go ahead to Menti, put in your votes, tell me what use cases you're most interested in. We'll, again, hone in on those today. And for anyone who does vote on other, there's the option for a chat in this presentation. So if you could just chat what other means to you, that'll help me know if I can comment on something during the program. All right, it looks like we have a good amount of answers in. Infrastructure planning being #1 response, maybe forecasting catching up a little as well. We'll definitely hit on those today. I'm actually, for these, I'm going to give a demo, in fact. So when we get to the end, we'll give a demo, and we'll even, for those interested, we'll give you the opportunity to use the demo and share it with your colleagues at your organizations as well. All right, so I wanted to have some fun today in the spirit of debunking myths. One of my favorite shows as a child was Mythbusters, and I don't know that it was really a lifelong career option for me or a career desire, but I just thought it would be funny if I played the host of Mythbusters EV style today. So I'm going to bring you 5 myths, and we're going to talk about, is it a myth? Is it a fact? And bust some myths. So starting off, first off is I would say a myth or something I hear a lot, which is I have DMV data. I can get the data, from some channel to see by zip code the count of electric vehicles. Or, oh, I have 100 customers enrolled in a telematics program and I can see those and then I can extrapolate. So that's sufficient. I think there are some nuances that we have to understand when thinking about analysis in this way. So before, again, if you all could just vote, tell me how you're currently identifying your EVs. I'm going to tell you, other ways you can, but I'm just curious, before we jump in, how are you currently identifying them? And this is typically this type of shape, I'll say, is when I talk to clients, I hear is that DMV data, especially because it's been around for so long and it's fairly available, has been a common one. And then customer surveys, I've also heard, obviously, I'll say customer surveys as well as enrollment data. For example, if a utility sees that a customer has purchased a level 2 charger, then 99% of the time they have an EV, right? So this is not surprising to see this distribution. Again, I would be curious about what the other is. And so if you wouldn't mind writing in the chat what the other is, that would be very interesting for me. All right, so here's, I'll say, the incumbent methods that we see and we talk to a lot of clients about. There's nothing wrong with these methods, right? Like, any piece of data you can get is important. It's more so these won't really solve your problem on their own. So essentially, you need to be looking at, how do I get the most value out of any data stream? So DMV data, that has been around, I would say, the longest. And essentially what you can get is the list of cars, and oftentimes you can get the model breakdown by zip code. The problem that I see with DMV data is essentially you can get sort of the growth charting. So I can see growth month over month or year over year, but I'm essentially missing the load shape in its entirety. So I don't understand the exact location of the vehicles on my grid. I don't understand the time of charging. I don't understand how they line up to my grid assets specifically. Unfortunately, it results in just, a generic type of outreach, and maybe I outreach heavily to this zip code, but it really doesn't give me the granularity that I need to make informed data-driven decisions. On the other hand, we see like surveys from customers or customers opting in or giving their data through APIs or telematics. Now, obviously, when I'm pulling data from a device itself, that's going to be very granular data, which we love. The problem is I have to get customers to opt into that data. Means that I really am going to see a very small portion of my population. And so that means that I have to extrapolate. again, I get the granular data, but I don't hit the full population. And extrapolation results in potentially wrong results, or potentially essentially like not using the data in the right manner. So what's our belief here? We're going to talk about the details of disaggregation in the next section. But one thing we believe is you need both broad coverage and granular coverage. Without those two, you're either going to have granular details, but that you have to extrapolate to your whole population, or you're going to have very generic details that is for your whole population, but you can't really do much with. And so when we look at this, the one advantage of using artificial intelligence or disaggregation is that you're both going to have high coverage across your entire territory for level 1 and level 2 vehicles. You're also going to have this huge depth of information that you'll see, what type of charger is it? When are they charging? What is their load profile? And that's why we don't believe that you can only rely on DMV data, or only rely on surveys, or only rely on car telematics. I do see, okay, I just saw someone comment in the chat, no questions yet. Feel free in the Q&A, if you do have questions that pop up, feel free to put them in there. So myth number 1 busted. You really need the complete set of information. And disaggregation is a good way to do that. So now I'm going to go into the details of disaggregation with another myth. So a lot of people think all disaggregation is the same. My analyst can probably just run some query and they can find the EVs, or this vendor can find it. The reality is that that is not true. You really need to think about far more things than just, is someone using a lot of energy? They must have an EV. There's many other layers to this data science puzzle. So before I get into the details, can I hear, is anyone currently having in-house resources working to detect EVs? You can answer yes, no, sort of, I'm not sure. I know this is pretty evenly spread from those that I've talked to. All right, looks like mostly no's, some sort of, some I'm not sure. I've seen a variety of different utilities have at least some partial effort to do this, but not always successful, and sometimes one-off experiments. And so what I wanted to do is really explain why that is, or why it's not as easy as you may think, by describing to everyone what is disaggregation, and specifically why a solution that has like very high precise, high recall, low disaggregation is going to be the best result. To do that, I want to explain what disaggregation is to start. Disaggregation is essentially the breaking apart of load in any premise. So that can be a business premise, residential premise. Essentially what Bidgely does, and we've been doing this for over 11 years now, is we're taking in all of these data points, in this case from smart meters, and we're plotting those data points over the course of a day, of a year. And so let's take, for instance, we have 15-minute granularity, 15-minute meters. What we see is that there'll be 96 points over the course of a day. And throughout the day, your electricity consumption is going up and down, and it's forming a unique shape. And the thing is that each appliance also has a unique shape, or a unique fingerprint that we can identify. When all of these appliances are overlaid on each other, it can be hard to identify. And so what our algorithms actually do is sort of peel away each layer of consumption. So the first thing we do is actually start with that always on consumption, where we remove, hey, what's always on in this household? And then we assign that to that always on bucket. Then we take heating and cooling. And the one thing about heating and cooling, those appliances are very much related to temperature. They also tend to have fans or compressors that have a cyclical on-off cycle. And so we then can assign, okay, this house has an air conditioning unit, and then it's using this much at this time period. Again, move that, assign that away to the air conditioning bucket. Then we have some other unique appliances that just have very interesting shapes. So a hot water heater, you see right here, it has just that very pointy shape because it's a high amplitude device. So those pull a lot of power. But generally, especially with instantaneous water heaters, they're just pulling it very quickly and then returning to normal. Electric vehicles, on the other hand, have high amplitude, but often spread over the course of a nighttime for many hours at once. Through this, we're actually able to detect every device in a customer's home, but we're also able to estimate how much that device is being used in terms of kilowatt hours at any time during the day. So how do we do this? It's not as pretty as that picture I showed you. It's actually through a large stack of machine learning algorithms that have been developed with ground truth and iteration over many years. So what we normally see is you see this graphic on the left. That is what we would just get if we formed a heat map out of a user's consumption. And how you want to read this is on the y-axis. That's actually every day in 1 year. On the x-axis, that's every hour in every day. So there's 24 points across the x and 365 across the y. The color coding is then indicating the high consumption. So the higher the KW, the higher or the more red that color is going to get. Through the stack of algorithms, we see that we can strip away all of the other appliances. And essentially, we are left with only EV instances or EV sessions. And what we can see is that you can see very clearly the start and end of that session. So you can see, does this customer charge 3 times a week? Are they charging at 9 kW amplitude? How much kWh are they using? And so we can start to actually form this user persona about their charging behavior. We can determine, so someone asked a great question on level 1 earlier. We can determine level 1 chargers as well. There's also a great chat in the chat thing here about, what about a hot tub that's only set to off-peak, in this case, starting at midnight. Now, that is actually a great case of that could be hard to detect. So when we look at level 2, our accuracy, precision, recall, which I'll walk you through, are going to be very, very high. When we do talk about level 1, an important thing is to note we will get slightly lower precision and recall because there's more devices that are going to have similar patterns. Now, with a hot tub, I would need to confirm with my data science team, but one thing, assuming that there's not too much interference that we'll see, is that won't have the same exact load shape. It's not just an on and across. It's going to have more of a cyclical load shape similar. We see this with pool pumps as well. Anything with a pump is going to have be more cyclical by nature. And so it does make it harder, which will reduce, these are machines, right? It'll make it harder to spot, which will reduce the output, but we can still see it even through that hot tub that's there. Other things, I'll say hot tubs, other things where you just do have a little bit more of the interference is a home with 2 air conditioners, for example. So then you have to really rely on the seasonal trends. Same with 2 heaters or a very large heat pump. But based on the historic data and then seeing those patterns, either cyclical or amplitude or behavior, we're able to at least a high degree of accuracy, precision, recall, determine the level 1, level 2, or even higher charger. So I wanted to touch very quickly on, well, is this really that hard? Like, do I just look for something that's really high in amplitude? Because I do know some utilities I've talked with, or even some competitors, just say like, oh, it's pretty easy. Like, it's not that hard to find an EV. That's not actually true. You know, like it requires certainly some advanced data science, and doing a generic methodology won't really serve you. So the detection problem is a common one. What I've seen is, oh, say anything above 6 kW or consecutive reads that are above 6 kW for this many times in a month, normalized temperature, and hey, I should just be able to see all my EVs, right? The problem with this is that can be misleading. So you might have the EVs in your population that you've identified, but you're also going to have a lot of false positives. And so later in this presentation, we're going to talk about like why it's bad to have too many false positives and what that does. But essentially doing a generic methodology, you're going to see over a 75% false positive rate. For example, we did this analysis. We did our disaggregation versus a simplified, just normalized and high consumption flag. And in the same zip code, we saw that the around the right detection rate we identified, which is around 4%, matching the DMV data. The generic approach ended up classifying 80% of homes as having EVs. That means that what we're going to see is, you know, what's the value in saying 80% of homes have an EV? Also, the reverse is true. So even if you do something like this, if you could only see if an EV charger was 6 kW and above, you actually miss a lot of the chargers because they might be level 1 or they might be like a lower amplitude level 2. And so when you think about, oh, can an analyst do this? Can a data scientist on my utility team do this? Be careful, because our team, I'll say we have over 30 data scientists. We have over 10,000 points of ground truth, homes of ground truth for EV only. And we've been iterating for over 11 years. So be cautious when you think about, oh, can an internal team do this? So another thing we see is there are vendors, you know, Bidgely is not the only vendor out there, and others may claim to have disaggregation. And I've heard this frequently. Oh, my vendor has, you know, 90% accuracy, 95% accuracy, so I don't even need to look any further. That's not, you know, that's not true. You need to really think about, what do I need to be doing and how good is my vendor? So first, before we get into it, let me know if you have a vendor today that's helping you with EV detection or disaggregation. But then what we'll talk about is, what do I really need to look for? So something that I'm going to walk through next is really this behind the scenes of the data science. And we are going to touch on the granularity here. I know that was another thing, the 15, 30, 60 minutes. How do those vary? But we're also going to touch on, in data science, what do I need to be measuring? How do I basically detail what success looks like in a data science classification algorithm? And so I'll let this go for just 30 more seconds, and then we'll get into actually, how do you know if a data science algorithm is good or is bad or is somewhere in between? All right. So this is, I want to flag, this is going to get a little bit technical. So feel free to chat me if I need to slow down or if I'm going too deep into the weeds. But to understand what an algorithm or any prediction, the success of that, you need to understand what's on the screen, which is called a confusion matrix. What a confusion matrix represents is the predictions an algorithm makes and then the actual result. So for the purposes of keeping it simple, we're going to say, hey, I'm a weather woman. I'm going to every day predict, will there be rain tomorrow? And, as my, I'll say, faithful audience, you assume I'm right most of the time, hopefully. So what we look at to see how often am I right, how accurate am I, how good of a weather woman am I, is we look at my predictions over time. And so on the left-hand side, you see, what are my predictions? Will there be rain or will there be no rain? On the x-axis, or that vertical piece, it'll have the actual. So did it actually rain or did it actually not rain? And essentially what you have to do to determine how good I am is compare, did I predict it was going to rain and it rained? That's a good prediction. That would be a true positive. Did I predict it was going to rain and then it didn't rain? Now this is a false positive, and this is very bad, right? If I predict it's going to rain, you're going to change your lifestyle. You're going to bring an umbrella. You may change your route to work. You may not take the bus. You might take a Uber, something like that. But that's like a significant difference, right, in what happened. There was no rain. Also, the other bad thing is if I say, oh, there's not going to be rain, go ahead, enjoy your day, make plans to go out to the park. But then there is rain, that's actually a false negative, and that's also a detrimental error. Finally, if I predict there's not going to be rain and there is not rain, then that was another successful prediction of a true negative. And so always think about classification problems in terms of this box. We can simply think about EVs in this way by replacing rain with the word EV. So do I predict the customer has an EV or do I predict they don't have an EV? And then do they actually have an EV or do they not have an EV? And so to measure our success, we use common metrics in data science. So these are the four most common metrics and ones you need to think about when thinking about electric vehicle detection and estimation and how you might use them. So the first is actually accuracy. I'll say it's the most generic term. Everyone wants to say, oh, accuracy, accuracy, accuracy. Essentially, this is the amount of true predictions I've made. So it's my true positives and true negatives over the total population. This is always the higher, the better, right? Then we have precision, which is essentially every time I say it will rain or there is an EV there, how many times am I correct? So out of all of the true, EV predictions, how many were true EV predictions or true positives? And again, we always want to maximize this. There's then recall, which is essentially of all the EVs in my territory, how many am I actually able to detect? So that is your true positives over your true positives and false negatives. And finally, there's your false positive rate. Again, your precision sort of hits at this, but this is specifically in my population, how many false positives am I hitting? So how many false positives plus true negatives are out there? So an important point in this, especially in EV classification, is the fact that EVs and the population is imbalanced. What I mean by that is EVs aren't a very popular thing yet. They're growing in popularity, but we see about an average of 1% to 2% penetration in any given region in the US, with obviously advanced regions being around 6%. This changes how we view success. Why I say that is I could make today, in a matter of seconds, an algorithm that basically says no one has an EV. And what that means is in a territory where there's 2% of EVs present, I would actually be having a 98% accuracy on that algorithm, just the way the math works. However, I wouldn't actually be detecting any EVs, so it wouldn't really be useful. On the other hand, if I use that generic approach, my accuracy would be absolutely terrible. So under 30%, because I'm assigning a bunch of people into the wrong bucket, but I would actually detect more EVs. And so the major takeaway here is don't just look at one accuracy number, actually understand what the success metrics are, what the precision, what the recall, what the accuracy, and what the false positive ratio is, to understand or determine how accurate an algorithm is. So I want to sort of give an example of something else that we can all relate to understand why you can't just rely on that accuracy number. So I'm going to use the example of identifying bad actors, right? People, let's just say people who want to cause harm to others. There's very minimal of them, right? But I want to catch them. If they go through a metal detector at an airport, let's say, or an event, the question is, how often are we detecting them to make sure everyone remains safe, but also how do we minimize the effect to everyone? You don't want to pull everyone aside and do a wand all over them. So again, here, I could actually build a solution that's 99% accurate by saying, here's just a wireframe that you walk through. It'll never catch anyone, but I can still claim there's 99% accuracy. But this doesn't meet the goal because you'd never actually be detecting these bad actors, and something very negative could happen if I'm not detecting them. On the other hand, same problem, detecting bad actors. Maybe I want to balance my precision, recall, and accuracy. And so now I want you to think about these terms in this example. So precision, that's essentially every time someone goes through the metal detector, I'm counting the number of times the metal detector is beeping, and then I'm counting the number of times when it beeped, it was truly a bad actor. So I'll say I go through airport security a lot. I often get beeped. I'm not a bad actor. And so, that was actually false. That's a false positive. But you don't want that to happen too many times. When you're detecting something, you want it to mostly be a correct detection. The second measure is recall. So this one, at least in this example, is very important because every time a bad actor passes through a metal detector, you really want it to beep. So it's essentially measuring how many of the bad actors who pass under the metal detector will be identified as a bad actor. So with this exact same setup, you can think about, this applies to EVs as well. So you can think about the metal detector as a Bidgely detection algorithm and think about it in the same way. And here, essentially, we want everyone with an EV to be detected, but we don't want to detect or say everyone has an EV or it's not really meaningful. And so I'm just wanted to show this slide. This is getting really technical, but when we think about an algorithm, we have these curves where we have a confidence score, or how likely is a customer to have an EV. And what we see is our true positives tend to be on that higher confidence score level. Our true negatives tend to be on the lower confidence score. And what we really need to do in order to optimize the precision and recall is play with the back and forth between the false negatives and false positives. And to do so, we need to think about what is better for the outcome? Is it better to minimize false positives? And that means we wouldn't be telling customers they have an EV if they don't, but we might be missing a lot of customers who do have EVs. Alternatively, you can say, no, it's really important that we get everyone who has an EV, even if we end up suggesting to many people that they do have an EV when they don't. In that case, we're designing for maximizing number of detections, minimizing false negatives, but we're going to increase false positives. And so what we do at Bidgely is actually this iteration where we choose what we want to accomplish. And our recommendation generally is when dealing with an end consumer, you don't want too many false positives. It really erodes the trust in the utility. And so you want to minimize the false positives. And then once you know the customer does have an EV, you can change the algorithm or change this balance so that you know they have an EV and really get a higher estimation value. So that I'm going to say that was the very quick primer on disaggregation. I'm going to go back. I do know someone actually had the question on both the granularity as well as the accuracy of level 1 versus level 2. So when we talk about these different metrics, Bidgely can detect level 1 and level 2 for 15, 30, and 60-minute data. However, they will have different metrics. So for example, our accuracy for 15-minute level 2 is over 98%, and our recall and our precision of are around 90%. That is going to decrease for 60-minute data. And then same with level 1. So like where our level 2 detection is above 98% accurate, above 90% precise. For level 1 detection, because there is more interference, what you're going to see is your accuracy is going to lower somewhere in the lower 90s, and then your precision and recall will actually lower all the way to somewhere between 70 and 80%. And so that doesn't mean it's inherently bad. What it means is you cannot use it in the same way. And that's when we're going to talk about the specifics of using the right data for the right use cases. So awesome. Some folks are already responding. I am curious. I know I went in a lot of detail, so I'm just curious if folks feel like that improved your knowledge, if it didn't. And I also want to say, if anyone is curious about this, you can always set up time with me. I'm happy to do a much longer review of how we do disaggregation, how we measure the success, because at the end of the day, that's the most important thing. We want to quantify to what degree we can detect and estimate. All right. So myth number 4. So this is really about what works for one case works for all, right? I don't need to think about, if I know one use case works, I don't need to think about the nuances of the other. So I think with anything, this is generally not true, but wanted to remind you of the 6 different use cases we talked about at the beginning, and just talk about how there can be nuances in use cases. That means that, like, hey, maybe something can work at a lower accuracy for targeted marketing, but it cannot for engagement. And so I'm actually going to use our level 1 detection and estimation algorithm as an example here. So targeted marketing, really trying to identify EV owners, be it level 1 or level 2, engage them, get them into a program, right? And so I don't really need to know many specifics about that customer. I just want to hope, hopefully we have good accuracy, low false positive rate, and they have an EV. With a level 1 detection, this is a mechanism we use, as well as level 2, but we feel comfortable marketing to level 1 owners to, for example, purchase a charger or participate in an EV managed charging program, because we're highly confident they do have a level 1 or they do have an EV charging on level 1. But we actually don't necessarily, or we're not as confident when it comes to the estimation of that usage. So I'll say when you're less sure, or when you have a lower confidence in AI, you always want to be cautious about what you tell to the customer, and you always want to phrase things in a more generic way. The reason being, when you have too many false positives in a hyper-personalized context, it creates a negative experience for the customer. And so when we go over to our EV customer engagement, which you see on the right, and this is actually informing the customer hey, you could save this much from time of use rates, you know, because we see that you're charging quite a bit in your peak period, and send them a notification that they charged in peak and could have saved this much money. We need to know that these numbers are highly accurate. Because they're highly personalized, it means customers take action. But when these numbers, or if these numbers were to be wrong, you'd have a very negative customer experience. And so it's not worth putting this out there unless you have very high accuracy, precision recall, and most of all, very good estimation. And so something I haven't talked about until now is the estimation piece, or understanding the hourly load of an EV at each hour. So what we see is that our estimation is actually also over 90%. So if I'm predicting that, you know, someone has an EV charging between the hours of 9 to 6 a.m. and I say they charged 27 kWh over that period, I'm within a 10% plus or minus there, which is very good and means that we can actually give them guidance on how do you save money, how do you optimize. Now, we don't actually do that for level 1 customers because our estimation is far worse. And what that means is we're not certain that we could give the right recommendation. And so this is where, when you have different use cases, you really need to think about your accuracy, precision, and recall in terms of the classification itself. But then you also need to think about what insights you put in front of the customer and how accurate those may be. Ultimately, for us, we always want to prioritize building that trust between the utility and the customer by putting real insights that are, you know, not doubted, doesn't cause concern, doesn't cause the negative moment with the customer. And so here's just an example going further into the image. The value of estimation is you can give your customer their actual bill in terms of EV, their actual usage within a peak or non-peak period. If you didn't have the high accuracy in terms of estimation, you could not do this. You would end up having so many calls into your call center. You would end up with just customers losing faith in your solution. But again, this really speaks to the accuracy of our solution. We have this running at a few utilities, and we actually see great customer feedback and no influx of calls because customers do see that this truly relates to their EV charging. Finally, I'm going to go to the demo portion of this. Something I hear a lot is like, this is great that you have all this data. We would love to know where our EVs are, but like, we don't really know how to use it. We don't have analysts, and they might need to do a lot of work. So we did realize that this was true at one point in time. Oftentimes, it's hard for everyone to be working off of that single source of truth in a utility. There's not always the tools needed. However, we've actually packaged all of our analytics into this easy-to-use tool that can serve anyone in the organization. And I'm going to actually demo that for you now to finish out our session. And I'm going to demo it for you on the use case of EV detection, specifically for infrastructure planning and analyzing on the grid. So give me one moment, I will pull that up. So it's actually impressive to think about this. Say you have 1 million customers in your territory. Each one of those customers has over 30,000 data points likely just from AMI. And then we take the estimation from every single device in the home, add that into our data. So we're crunching over, you know, billions of data points in this tool, but we make it really easy for analysts and program managers alike to use the tool and to actually make data-driven decisions with it. So what I'm showing you now is what we call Analytics Workbench. And what this does is we house all the data in Snowflake, and then we visualize all of the data with Looker on top of it. And this is just a demo account that I'm showing you. And so it has about 17,000 accounts, and it composes, or those accounts over the past year made up 269 gigawatt hours of consumption in this territory. The great thing about this tool is that anywhere in the tool, you can simply click and add a filter. So what I'll show you is I am a program manager, and I'm really interested in understanding the EV load shape, as well as the customers who do have EVs in my territory. To figure that out, all I have to do is simply click EV. So with a single click, you see up in the upper corner, I've applied this filter, it's running. And what I'm going to be able to understand is where those customers are located geographically, where those customers are located on the grid, what their load shape is on the grid. And then also I can even, for example, say I have a managed charging program, I can even select the exact customers who are most likely to give me the most amount of load in my peak hours. And so I'll show you here, once this runs, I'm able to use this consumption decile chart to say, I only want to see the top 10% of EV consumers, because those are the consumers I want in my program. We also work with utilities to actually map their grid assets, so their substations, feeders, or transformers, to customers. What this enables us to do is actually see where electric vehicles fall on the network, and most importantly, see the load shape that is occurring on each of these assets. I can, once we let this run to completion, so now we're starting to see the EV load shape, the ownership trend, as these come through, the differences in amplitude, the distribution on a map, and then we'll be able to see down here the actual 8760 of that EV charging, but even see the impact on the grid itself. And all I had to do was click a few buttons, and then I'm essentially, very easily getting results, sharing that with my colleagues, sending it to management. Is all housed in one place that's simply used by everyone in my team. One thing I want to mention before we all depart is that actually this demo environment, anyone is welcome to use this. So if you're interested in exploring, what queries you may run, what would be available, we can actually give this to you, and you can play around with it so you could understand what you might do in your own organization. So now I'll just go to the Menti again. We'll finish up with just some feedback, and I'm happy at this time to also answer any questions you may have. Always love hearing feedback, hearing questions, so let us know what you're interested in. Great question, Jan. So I think it's actually my machine. Everything loads. You're noting it takes a while for 100,000 customers. Everything does load. My computer is running fairly hard right now, but the system is designed for everything to load for any query within a minute, and for any even complex query within 2 minutes. And we size our environment. So it is very data intensive, to be honest, but we size based on the number of meters for that utility. So for example, we have a utility with 1.7 meters on our platform, and we size that accordingly so that they can process and not just wait for, you know, all of that to come through. Any other questions? All right, if I could then just get everyone's feedback, we'll go to the last piece of this. I'm actually not sure why Menti isn't wanting to start for me. So if everyone, I'd appreciate, just send us notes, send us chats. Thank you so much for joining. I'd love feedback from the audience. I'd love feedback via email, via Zoom chat, anything. And then if you're interested in a follow-up conversation, most importantly, please reach out to us. We'd love to go into a deeper dive of our disaggregation and the solutions. And thank you. And yes, April, this will be available to view again. Excited, you know, to have you watch it again, but of course also reach out if you're interested in a one-on-one workshop or discussion. We're always happy to, you know, give broader teams with your organizations this information. Thanks everyone for attending. Sorry for that technical difficulty at the end, but really appreciate everyone's attention and great questions. Thank you.